My name is Catherine Stalter, and I'm one of the people you'll be seeing on this videotape reviewing every aspect of the high school algebra math curriculum. We are backed by a team of educators who have put together a powerful learning tool incorporating computerized techniques which can quickly and efficiently allow us to visualize math concepts for you. Think of us as your own personal math tutors, available whenever you'd like to review concepts and techniques in math. Before we get started, I have some advice that can help you get the maximum benefit from this tape. First of all, this material is designed to complement, not replace, classroom instruction. Unless you have exposure to these concepts in a classroom setting with a good teacher and a good textbook, you're likely to find the pace of this presentation too rapid. The key word here is review. Very few people will be able to use the videotape in place of formal classroom instruction. Next, please, don't fall into the trap of regarding this as being similar to any other kind of television. We are all in the habit of letting our brains sort of go to sleep whenever we're in front of the tube. The material presented on this tape concentrates weeks of work into just a few minutes. You must be ready to concentrate on what is shown and said. Take frequent breaks. Perhaps 20 minutes at a time is as much as most people can devote to material like this without at least a short change of pace. Whenever you feel yourself starting to lose concentration, it's time to turn off your machine. Get some fresh air, do some physical exercise, or perhaps get something to eat. The important point is you're in control. We'll always be here when you get back. Which is my next point. In order to really get the most from the videotape, you should get used to the idea of using the controls of your VCR to help you get the information you need. Use your remote control, if you have one, or sit close to the machine if you don't. Be ready to pause, rewind, and replay sections over until you are comfortable with the concepts we present. In connection with that, have a pencil and paper handy. You should feel free to pause your VCR and write out some of the material we'll be presenting for yourself. Working out problems for yourself will increase your mastery of the topics. Try to make the experience of using this tape as interactive as possible. If you remain a passive viewer, I'm afraid this will be less valuable to you. If you have the VTS manual, the workbook which accompanies our videocassette tape, use it extensively in your review. You'll find that your mastery of this material will rapidly increase in this way. One last comment. As you go through the tape, write down a counter number from your VCR for those portions of the tape that you think you'll need to review later on, so you'll be able to find things easily on the tape later. Remember to set your VCR counter to 0 each time you use the tape. So, while you're getting ready, set right near your VCR with a pencil and some paper, you can shut off your machine and take your first break before we begin our first review topic.
We will now learn 4 basic methods of factoring. First, factoring a number. Second, factoring out a letter or a variable. Third, factoring the difference between 2 squares. And fourth, factoring a trinomial. First, let's look at factoring out a number. If we have the binomial 6x minus 18, we have 2 terms, and we try to find a number that goes into both terms. The largest number that goes into 6 and 18 is 6, so we factor out the 6. And what's left? 6 times what gives us back 6x minus 18? The answer is x minus 3. And the reason for that is 6 times x is equal to 6x, and 6 times negative 3 is equal to negative 18. And so our final answer is 6 times x minus 3. Now, let's factor out a letter or a variable. X squared minus 8x. Can you factor out a number from the x squared term and the 8x term? The answer is no, because the number in front of the x squared is 1, and the number in front of the x is negative 8. Except for the number 1, there is no number that goes into 1 and 8. So we try to factor out a variable. Now, what variable can we pull out from x squared and x? The answer is x. And then we ask ourselves, x times what will give us back x squared minus 8x? And the answer is x minus 8. And because x times x is x squared, and x times negative 8 is equal to negative 8x. And so our final answer is x times x minus 8. On the screen, you now see 6x squared minus 18x. To factor this, we will first try to factor out a number, because we always try to factor out a number first. The largest numerical factor is again 6. 6 goes into 6 and into 18. What can we factor out of x squared and x? What variable? The answer, x. So we have 6x factored out. And then we ask ourselves, 6x times what will give us back 6x squared minus 18x? And the answer is x minus 3, because 6x times x is 6x squared, and 6x times negative 3 is negative 18x. And so our final answer is 6x times x minus 3. The next example has 3 terms: 18x cubed, y to the 4th power, z to the 5th power, minus 12x squared y cubed, z to the 4th power, plus 6x squared y squared, z squared. Quite a formidable problem, but you can handle it. First, we try to factor out the largest number from all 3 terms, and that's 6. 6 goes into 6, and into 18, and into negative 12. What's the largest power of x that all the terms have? Well, that's x squared. And for the y's, it's y squared. And for the z's, it's z squared. Now, 6x squared, y squared, z squared has been factored out. And now we ask ourselves, 6x squared, y squared, z squared times what number will give us our first term back again? And the answer is 3xy squared z to the 3rd, because 6 times 3 is 18, x squared times x is x to the 3rd, y squared times y squared is y to the 4th, and z squared times z to the 3rd is z to the 5th. And so our first term is 3x y squared z to the 3rd. And now we ask ourselves, 6x squared y squared z squared times what number will give us back our second term, negative 12x squared y to the 3rd z to the 4th? And the answer is negative 2yz squared, because 6 times negative 2 is equal to negative 12, and x squared is already up there and is out there, so we don't have to multiply it by anything. We go on to the next term, which is y squared. Y squared times y is equal to y to the 3rd, and z squared times z squared is equal to z to the 4th. And now we come to the third term, 6x squared y squared z squared. 6x squared y squared z squared times what number will give us back 6x squared y squared z squared? And the answer is 1. I'll bet you guessed it. The reason for that is that 6x squared y squared z squared times 1 is equal to 6x squared, y squared, z squared. Be sure that you put that positive 1 at the end. The term we factored out times 1 will give us the last term. The third method of factoring concerns the difference of two squares. This is factored into the square root of the first term plus the square root of the second term times the square root of the first term minus the square root of the second term. Take, for example, x squared minus 9, or x squared minus 3 squared. Notice that x is being squared and 9 is really 3 squared. So we get x plus 3 times x minus 3. Now let's factor x squared minus 100. This is the difference of two squares. Therefore, the factors are x plus 10 times x minus 10. Now let's try to factor 2x squared minus 18. First, we try to factor out a number, and the largest number that goes into both terms is 2. So we factor out the 2. Can we factor out a variable? No, because the second term, 18, has no variable. So we factored out the 2, and we're left with x squared minus 9. Now we try to factor x squared minus 9, which is equal to x plus 3 times x minus 3. And the final answer is 2 times x plus 3 times x minus 3. Now we'll move on to trinomials. Let's factor x squared plus 5x plus 6. We use the reverse of the FOIL method of multiplication. We start by drawing two sets of parentheses. Next, we have to look at the first term, x squared. What times what gives you x squared? X times x. So we place the x's in the two parentheses as indicated. Then we look at the last sign. If it's positive, then the two signs in the answer must be both positive or both negative, because a positive times a positive is a positive, and a negative times a negative is a positive. To find out which pair we use, we look at the sign of the middle term. If the middle sign is positive, we use two positives. If it's negative, we use two negatives. In this case, it's positive, so we put plus and plus next to the x's in the parentheses. Now we take the last number, 6, and we find all the factors of 6, which are 1 and 6 and 2 and 3. Now we go back to the two parentheses. If we have chosen already two pluses or two minuses, then we have to have a pair of factors that add up to the coefficient of the middle term, which in this problem is 5. The pair 2 and 3 add up to equal 5. So these are the factors we use. Our final answer is x plus 3 times x plus 2. The next example is x squared minus 5x plus 6. We look at the last sign. It's plus. Then we look at the first sign, and that's minus. So now we have x minus and x minus. We get the factors of 6, which are 1 and 6 and 2 and 3. Now, since we have two minuses in our answer, we choose 2 and 3 because that's the pair of factors that add to the number in the middle, 5. And the answer is x minus 2 times x minus 3. Our next example is x squared minus x minus 6. To factor this, we put x and x in the parentheses. We look at the last sign, and it's minus. So now we use a plus and a minus, since a positive times a negative is a negative. We get the factors of 6 again, and that's 1 and 6 and 2 and 3. And since we've used one of each sign in the answer, a plus and a minus, we want the pair of factors whose difference is the same as the number in the middle, which is a minus 1. And again, it's 2 and 3. The difference of 2 and 3 is 1. Since the first sign is minus, we put the bigger number, the 3, next to the minus and the 2 next to the plus. And the answer is x plus 2 times x minus 3. Now we'll factor x squared plus x minus 6. Again, we look at the last sign, and it's minus. So we're using a plus and a minus. But now, after we get the factors of 6, we have to get again the ones with a difference of 1, which is 2 and 3. But the middle term has a plus 1, so the bigger number, 3, goes next to the plus. And the answer is x plus 3 times x minus 2. The next example is x squared minus 10x minus 56. To factor this, we first look at the minus at the end, the sign of the third term. Since it is minus, we use a plus and a minus in our answer. We have x plus and x minus. Now we take the factors of 56, which are 1 and 56, 2 and 28, 4 and 14, and 7 and 8. Now we look at the two signs, and we see that we have plus and minus in our answer. Therefore, the pair of factors must subtract to the number in the middle in our problem, which is 10. Which pair of factors has a difference of 10? The answer is 4 and 14. Which one goes where? Well, we look at our original trinomial, and the middle term is minus 10x. So the bigger number, the 14, will be next to the minus, and the 4 will be next to the plus. We have x plus 4 times x minus 14. Of course, your solutions aren't going to come as easily to you as they do here for us on the tape. You'll have to work them out for yourselves with pencil and paper. And now, let's summarize the method for determining the signs of the factors when we factor a trinomial. These are the two signs of a trinomial. The two signs separate the three terms of a trinomial. First, you look at the last sign. If the last sign is plus, then you know that you need two pluses or two minuses. You look at the first sign. If the first sign is plus, then you know that you need two pluses in your answer. If the first sign is minus, then you know that you need two minuses in your answer. What you must remember is that if the last sign is plus, you need either two pluses or two minuses in your answer, and the first sign tells you whether to use two pluses or two minuses. Now, if your last sign is a minus sign, then you know that you need a plus sign and a minus sign in your answer. The order of the plus and minus sign does not matter, but you must have a plus and a minus sign. The first sign tells you that the larger number must have a plus sign in front of it, or it must have a minus sign in front of it. Once again, if the last sign of your trinomial is minus, then you know that you have a plus and a minus in your answer, and the first sign tells you what the sign of the larger number should be. If we have a problem like x squared minus 81 equals 0, this is called a quadratic equation. That's because we have an x term to the second power, and the expression, in this case a binomial, is equal to 0. We factor x squared minus 81. That's the difference of two squares. So it factors to x plus 9 times x minus 9 equals 0. Now before, we would stop here and have x plus 9 times x minus 9. That's x squared minus 81 factored. But now, because it is set equal to 0, we go further. The only way the product of two numbers can be 0 is if at least one of them is 0. Hence, if two factors have a product which is equal to 0, then one of the factors, or both factors, must equal 0. This is called the zero product theorem. Therefore, we set each factor equal to 0 to see what solution it may suggest for the original equation. Each factor is set equal to 0. X plus 9 equals 0, and x minus 9 equals 0. We solve each equation separately, and we get two answers. In this case, negative 9 and positive 9. So, our solution set is 9 and negative 9. In our next example, x squared minus 7x plus 12 equals 0. We factor and get x minus 3 times x minus 4 equals 0. We set each factor equal to 0 and solve. X minus 3 equals 0 results in x equals 3, and x minus 4 equals 0 results in x equals 4. Our solution is 3 and 4. Our next problem is x squared minus 7x equals negative 10. We add 10 to both sides of the equation, which results in x squared minus 7x plus 10. We factor the quadratic equation and solve for x. X minus 2 equals 0, so x equals 2. And x minus 5 equals 0, giving us x equals 5. 2 and 5 are the solutions.
We sincerely hope that you found this tape useful. And for all of us here at VTS, we wish you the very best of luck in all of your academic endeavors. Hello, my name is Catherine Stalter, and I'm one of the people you'll be seeing on this videotape reviewing every aspect of the high school algebra math curriculum. We are backed by a team of educators who have put together a powerful learning tool incorporating computerized techniques which can quickly and efficiently allow us to visualize math concepts for you. Think of us as your own personal math tutors, available whenever you'd like to review concepts and techniques in math. Before we get started, I have some advice that can help you get the maximum benefit from this tape. First of all, this material is designed to complement, not replace classroom instruction. Unless you have exposure to these concepts in a classroom setting with a good teacher and a good textbook, you're likely to find the pace of this presentation too rapid. The key word here is review. Very few people will be able to use the videotape in place of formal classroom instruction. Next, please, don't fall into the trap of regarding this as being similar to any other kind of television. We are all in the habit of letting our brains sort of go to sleep whenever we're in front of the tube. The material presented on this tape concentrates weeks of work into just a few minutes. You must be ready to concentrate on what is shown and said. Take frequent breaks. Perhaps 20 minutes at a time is as much as most people can devote to material like this without at least a short change of pace. Whenever you feel yourself starting to lose concentration, it's time to turn off your machine. Get some fresh air, do some physical exercise, or perhaps get something to eat. The important point is you're in control. We'll always be here when you get back. Which is my next point. In order to really get the most from the videotape, you should get used to the idea of using the controls of your VCR to help you get the information you need. Use your remote control if you have one, or sit close to the machine if you don't. Be ready to pause, rewind, and replay sections over until you are comfortable with the concepts we present. In connection with that, have a pencil and paper handy. You should feel free to pause your VCR and write out some of the material we'll be presenting for yourself. Working out problems for yourself will increase your mastery of the topics. Try to make the experience of using this tape as interactive as possible. If you remain a passive viewer, I'm afraid this will be less valuable to you. If you have the VTS manual, the workbook which accompanies our videocassette tape, use it extensively in your review. You'll find that your mastery of this material will rapidly increase in this way. One last comment. As you go through the tape, write down the counter number from your VCR for those portions of the tape that you think you'll need to review later on, so you'll be able to find things easily on the tape later. Remember to set your VCR counter to 0 each time you use the tape. So, while you're getting ready, set right near your VCR with a pencil and some paper, you can shut off your machine and take your first break before we begin our first review topic.
Is the algebraic solution of two equations simultaneously. In other words, finding values for the unknown variables that make both equations true. There are two ways to do this, by substitution and by elimination. Let's do an example using substitution. In the substitution process, we take one equation and solve for one variable in terms of the other. Then, we substitute that expression in the second equation. Here's the example. Note that the second equation gives us an expression for y in terms of x. So, we can simply substitute x plus 5 for y in the first equation. Substituting, we get 2x plus x plus 5 equals minus 1. Combining like terms and solving, we get x equals minus 2. Now, we take this value for x and substitute it in y equals x plus 5. We get y equals minus 2 plus 5, which is equal to 3. So, our solution is x equals minus 2 and y equals 3. We check this solution by substituting these values in both equations. 2x plus y equals minus 1, and y equals x plus 5, with negative 2 for x and 3 for y. Here we check the first equation. It checks out. Now let's check the second. It also checks out. Now, if the solution hadn't checked out, then we may have made a mistake. Now that we've solved two simultaneous equations using the substitution process, that is, by substituting the second equation's value for y in the first equation, let's use the elimination process in the same example. In this process, we eliminate one of the variables from both equations and solve for the remaining variable. Here, we first rewrite y equals x plus 5 so the x is on the same side of the equation as y, getting negative x plus y equals 5. Line up the two equations as shown here, with the x and the y terms above each other. You can see that the y's will be eliminated if we can just change the signs and add them together. So let's subtract. Changing all the signs in the bottom and combining the y's cancel out. And we get 2x plus x, 3x, equals minus 6. Now we have eliminated the y's, so we can solve for x. Doing so, we get x equals -2. Substituting -2 for x in the original equation, we get the same answer as before. Y equals 3. That's the solution. Now, the solution, let's call it S, can also be written as S equals x comma y, or in our case, -2 comma 3. It's another way of expressing our answer. Let's do another problem. In this problem, here, by simply adding the two equations together, the y's will be eliminated. We get 3x equals 6. So, x equals +2. We then substitute x equals 2 into either one of the two original equations and solve for y. Solving, 2x plus y equals 5. We get y equals 1. So, our answer is x equals 2 and y equals 1. Here's another problem. But in this problem, we can't just add or subtract the equations because we wouldn't eliminate either of the variables x or y. So let's first try substitution. We can get one variable alone in terms of the other variable by adding 2y to both sides. We get x equals 6 plus 2y. Now, substituting this expression for x in the first equation, we get 3 times 2y plus 6 plus y equals 4. Multiplying out and solving for y, we get y equals -2. Substituting this value for y in the expression for x, we get x equals +2. The answer, x equals 2, y equals -2. Now, to use the method of elimination, we first have to get one variable's coefficient the same in both equations. Let's line up the two equations and try to get the y values to be the same. If we multiply the first equation by 2, we get 6x plus 2y equals 8. Now, by adding the two equations, the positive 2y and the negative 2y will cancel out. We'll get 7x equals 14, or x equals 2. Remember, when you multiply one or more of the equations, be sure you multiply the right side by the same number that you multiply the left side. So now we substitute the value we got for x in one of the equations and solve for y. We get y equals -2. All simultaneous equation problems should be checked by substituting the solution in both original equations. So, we take our solution and we substitute. It checks. And it checks again. The real numbers are assigned as coordinates to points on a number line, which we draw as a horizontal line. Another number line is introduced perpendicular to the first one at 0, the origin. The horizontal line is called the x-axis. The vertical line is the y-axis. Every point in the plane lies on the axis or in the 4 quadrants into which the axes divide the plane. Normally, we assign the same unit to both axes. The point P shown has coordinates 3, 4. Note that the x-coordinate, or abscissa, is given first, and the y coordinate, or ordinate, is given second. We'll now turn to solving equations graphically. The equation of a line is often written as y equals mx plus b. It's called the slope-intercept form of the equation of a line. M is called the slope, and b is called the y-intercept. B is the y-coordinate of the point where the line intercepts or crosses the y-axis. That is, where x equals 0. When x equals 0, y equals mx plus b gives y equal b. For example, if a line crosses the y-axis at 0, 3, then b equals 3 is the y-intercept. The slope, m, of the line measures the steepness of the line, its rise or fall. It is the change in y over the change in x. This line has a positive slope because it rises. Y increases as x increases. This line has a negative slope because it falls. Y decreases as x increases. A horizontal line has 0 slope because y does not change. A vertical line has no slope because the change in x is 0, and we may not divide by 0. The slope m may be written as delta y, the change in y, divided by delta x, the change in x. Delta y is the difference of the y-coordinates of 2 points on a line, y2 minus y1. And delta x is the difference of their x-coordinates. Note that we'll get the same slope m no matter what 2 points we use on the line. Let's try an example. In the equation y equals 3x plus 2, what's the slope? Right, the slope is 3. It's the coefficient of the x term when y is alone. If the equation is 2x plus y equals 5, then we first must get the y alone. We subtract 2x from both sides, and we get y equals negative 2x plus 5. Now, the coefficient of the x term is negative 2, and that's the slope. What is the y-intercept? Well, set x to 0 in y equals negative 2x plus 5. The b position is plus 5, which means that the line of this equation crosses the y-axis 5 units up. Incidentally, if you have the workbook and manual from VTS, use it to review this tape and to do some extra problems. Parallel lines are 2 lines in the same plane that never meet. Parallel lines have the same slope. Are y equals 4x minus 2 and 4x plus y equals 7 parallel? No, since the slope of the first line is plus 4. And when you get y alone in the second equation, you get y equals negative 4x plus 7. So you see that the slope of the second line is negative 4. Since the slopes are not equal, the lines are not parallel. Here's our first problem in which we solve 2 equations graphically. First, we must get each equation into the form y equals mx plus b. In other words, we must get the y's alone. In the first equation, we'll divide each term by 2. This gives us y equals x over 2 plus 3. As we make our chart, we'll take values of x that are multiples of the denominator. Since the denominator is 2, we'll use 0, 2, and then 4. Substituting these values for x into the equation, we get, for x equals 0, y equals 3. For x equals 2, y equals 4. And for x equals 4, y equals 5. Thus, we get our 3 points: 0, 3, 2, 4, 4, 5. We plot those 3 points on a graph. We connect the points with a straight line. If the points form a straight line, then we know we've done a good job. We draw arrows at the end as we extend the line. And on the line itself, we write the original equation. 2y equals x plus 6. Now, we'll graph the second given equation. 3x minus y equals 2. We get y alone by subtracting 3x from each side and multiplying everything by -1. This gives us y equals 3x minus 2. We take values 0, 1, and 2 as values for x. We could have taken any values, but those are pretty easy to use. Substituting x is 0, we get y is -2. Substituting x is 1, we get y is 1. And substituting x is 2, we get y is 4. We plot these 3 points on the graph. We connect the 3 points, get a nice straight line, and we extend it with arrows at the end and label the line with the equation. Y equals 3x minus 2. We see that the 2 lines cross at the point 2, 4, and we label that. That point is the point of intersection, and its coordinates give the answer to the problem. X equals 2 and y equals 4. That should solve both equations. We must check the solution in both equations. So, we substitute the obtained values for x and y in the original equation. It solves. Our solution is correct in the first, and it checks in the second. So, both equations are satisfied by our solution, x equals 2 and y equals 4. Here's our next problem. How do we graph x is greater than 2? Well, whenever you have an equation where x equals some value, that's a vertical line. So, since this is x is greater than 2, we'll change it to x equals 2, and we'll draw that vertical line through the point 2 on the x-axis. Now, we're only interested in the points on one side of that line, not the points on the line itself, because there's no equal to. So, the vertical line at x equals 2 is a dotted line. And we shade the region to the right of x equals 2, since all the points in this region have values of x greater than 2. If we want to graph y is less than or equal to 2, the y equals 2 is a horizontal line through point 2 on the y-axis. You can draw a solid horizontal line, since we have here y is less than or equal to. Since we want the points less than 2, we'll also shade all the area below that horizontal line. Now, let's solve 2 inequalities by graphing. We do so by first solving the corresponding equalities. We take the first inequality. Y is less than x minus 2. And replace the less than by an equal. It becomes y equals x minus 2. We make a table and we choose values for x, 0, 1, and 2. And by substituting these values in x minus 2, we get the respective y values. We get 3 points, 0 minus 2, 1 minus 1, and 0, 2, 0 rather. These are our 3 points, and we can now plot them. We connect these 3 points with a straight line, and we label the line with the equation. Now, since we are concerned with an inequality here, we must shade the region that corresponds to the inequality. Remember, the points on the line make y equal to x minus 2. We don't want that. We want the original inequality, y is less than x minus 2. The line divides the plane into 2 parts, only one of which would satisfy the inequality. So, choose a point on one side of our line and see if it satisfies. Because it's so easy to use, let's choose the point 0, 0, the origin, and substitute it into the original inequality. It yields 0 is less than 0 minus 2, or 0 is less than negative 2. Well, that's false. Therefore, we do not want the points on the same side of the line as 0, 0. So, we shade the other side of the line, the area below the line. Now, we go back to the second inequality. Y is greater than or equal to minus 2x plus 4. And again, we replace the inequality sign with the equal sign. And we get y equals minus 2x plus 4. We make a table using 1, 0, and 2 for x. And we get the corresponding values of y. These are 4, 2, and 0. So our points are 0, 4, 1, 2, and 2, 0. Now we can plot these 3 points, connect them, and label our line. Now, we must also shade one side of this line. We take the point 0, 0 again and substitute it into the original inequality. Y is greater than or equal to negative 2x plus 4. Becomes 0 is greater or equal to negative 2 times 0 plus 4. 0 is greater than 4. That's also false. Again, we're not interested in the region on the side of the line that has the point 0, 0 on it. So we shade in the other side of the line. Now, the area where the two shaded regions cross each other, right here, this cross-hatched area, represents our solution. There's one little change that we must make before our answer is complete. Remember that the first line that we drew was the line y equals x minus 2. But we're only interested in y is less than x minus 2. We do not want to include the points on the line in our solution. So our original line should have been drawn dotted. The dotted line tells us that the points on the line are not included in our solution set. The second line, however, is solid because that expression has that little extra equal in it.
We sincerely hope that you found this tape useful. And for all of us here at VTS, we wish you the very best of luck in all of your academic endeavors. My name is Catherine Stalter, and I'm one of the people you'll be seeing on this videotape reviewing every aspect of the high school algebra math curriculum. We are backed by a team of educators who have put together a powerful learning tool incorporating computerized techniques which can quickly and efficiently allow us to visualize math concepts for you. Think of us as your own personal math tutors, available whenever you'd like to review concepts and techniques in math. Before we get started, I have some advice that can help you get the maximum benefit from this tape. First of all, this material is designed to complement, not replace classroom instruction. Unless you have exposure to these concepts in a classroom setting with a good teacher and a good textbook, you're likely to find the pace of this presentation too rapid. The key word here is review. Very few people will be able to use the videotape in place of formal classroom instruction. Next, please, don't fall into the trap of regarding this as being similar to any other kind of television. We are all in the habit of letting our brains sort of go to sleep whenever we're in front of the tube. The material presented on this tape concentrates weeks of work into just a few minutes. You must be ready to concentrate on what is shown and said. Take frequent breaks. Perhaps 20 minutes at a time is as much as most people can devote to material like this without at least a short change of pace. Whenever you feel yourself starting to lose concentration, it's time to turn off your machine. Get some fresh air, do some physical exercise, or perhaps get something to eat. The important point is you're in control. We'll always be here when you get back. Which is my next point. In order to really get the most from the videotape, you should get used to the idea of using the controls of your VCR to help you get the information you need. Use your remote control, if you have one, or sit close to the machine if you don't. Be ready to pause, rewind, and replay sections over until you are comfortable with the concepts we present. In connection with that, have a pencil and paper handy. You should feel free to pause your VCR and write out some of the material we'll be presenting for yourself. Working out problems for yourself will increase your mastery of the topics. Try to make the experience of using this tape as interactive as possible. If you remain a passive viewer, I'm afraid this will be less valuable to you. If you have the VTS manual, the workbook which accompanies our videocassette tape, use it extensively in your review. You'll find that your mastery of this material will rapidly increase in this way. One last comment. As you go through the tape, write down a counter number from your VCR for those portions of the tape that you think you'll need to review later on, so you'll be able to find things easily on the tape later. Remember to set your VCR counter to 0 each time you use the tape. So, while you're getting ready, set right near your VCR with a pencil and some paper, you can shut off your machine and take your first break before we begin our first review topic. If a car traveled at a rate of 50 miles per hour in 3 hours, it traveled 3 times 50 or 150 miles. The three quantities which are related are the distance traveled, 150 miles, the rate of speed, 50 miles per hour, and the time traveled, 3 hours. The relation involving the distance, d, the rate, r, and the time, t, may be expressed in the following ways. d equals r times t, t equals d over r equals d over t. In our problems, rate will represent 1. The uniform rate of speed, a speed which will remain consistent throughout the trip. For example, a car traveling at 50 miles per hour on a 3-hour trip, the car is constantly traveling 50 miles per hour. Number 2, the average rate of speed, which represents the total distance traveled divided by the total time traveled. For example, a car which traveled 150 miles in 3 hours was traveling at an average rate of 150 divided by 3, or 50 miles per hour. In solving motion problems, it is helpful to draw a diagram. The facts may be organized by using verbal sentences or by using a table as well. There are different kinds of motion problems. The first being opposite direction. Our first example says two trains leave the same station at the same time and travel in opposite directions. Their rates are 40 miles per hour and 30 miles per hour respectively. In how many hours will they be 420 miles apart? Draw a picture. Then we fill in a table. We label the two lines of our table, train 1 and train 2, and enter in the rate in the appropriate boxes, 40 and 30. The trains are starting at the same point and going in opposite directions. The problem will be finished when the trains are 420 miles apart. This means that the two trains are starting at the same time and are finishing at the same time. So we let x equal the number of hours traveled, and since each train travels x hours, we put in x in the time column for each train. To get the distance box, we multiply the rate times the time. 40 times x equals 40x, and 30 times x equals 30x. The two distances together add up to the total distance, 420 miles. So we write our equation. 40x plus 30x equals 420. Combining like terms, we get 70x equals 420. Dividing by 70, we get our answer of x equal to 6. So 6 is the number of hours traveled by each of the trains. A variation to this type of problem is if the question had been worded at the start this way. If two trains leave the station at 7 a.m. and travel in opposite directions, and if their rates are 40 miles per hour and 30 miles per hour, at what time of the day will they be 420 miles apart? This is the same question as before, except we want to know the actual time that the trains finish traveling. If they start at 7 a.m. and it took them 6 hours to be 420 miles apart, their final stopping time is 1 p.m. Another variation goes like this. How far did train 1 travel? Well, by far we mean distance. So we check the distance box for train 1. 40x. But x came out to be 6 hours, so 40 times 6 means that train 1 traveled 240 miles. Example 2. Two planes are 5,150 miles apart. At 9 a.m. they start traveling towards each other at average rates of 450 and 580 miles per hour. At what time will they pass each other? Here the two planes are starting at different places and going towards each other. They are still covering the total distance between them, which in this case is given as 5,150 miles. The two distances will have to be added up to get the full distance of 5,150. So we make a table and label the planes fast plane and slow plane. We fill in the rates. We let x equal the number of hours traveled. Since each of the planes is traveling the same number of hours, they are both starting and stopping at the same time. Multiplying the rate times the time, we get 580x for the fast plane's distance box and 450x for the distance traveled by the slow plane. We add the distance boxes together. 580x plus 450x equals 5,150. Combining like terms, we get 1,030x equals 5,150. We divide by 1,030 on both sides of our equation and get an answer of x equaling to 5. It took 5 hours for the planes to be 5,150 miles apart. Since they started at 9 a.m. and they traveled for 5 hours, they finished at 2 p.m. Example number 3. Two boats start from two ports 320 miles apart and sail towards each other. One sails at 35 miles per hour and the other at 45 miles per hour. In how many hours will the boats still be 40 miles apart? In other words, in how many hours will they have traveled 280 miles? We set up our table. 45 and 35 are the rates, and each boat travels x hours. The distances are 45x and 35x. Now we add the distances 45x plus 35x and set it equal to 280. 45x plus 35x equals 280. Combining like terms, we get 80x equals 280, and dividing by 80 on both sides of the equation, we get an answer, x equals 3 1/2. So each of the boats traveled for 3½ hours. Our next problem. Two trains started at the same time from the same terminal. One traveled west 30 miles per hour faster than the other train, which was traveling east. After 5 hours, they were 450 miles apart. Find the rate of each train. This problem differs from the last three problems in that here we know the time traveled, but we have to find the rates. The time traveled for each of the trains is 5 hours. We let the train traveling east have a rate of x miles per hour, and the rate of the train traveling west at 30 miles per hour faster than the first train be x plus 30. To find the distance box, we multiply rate times time, and we get 5x plus 150 for the train traveling west and 5x for the train traveling east. We add up the two distances, 5x plus 150 plus 5x, and set this equal to 450 miles. We combine like terms, get 10x plus 150 equals 450, and subtract 150 from both sides, which leaves us with 10x equals 300, and x equals 30. So the rate of the train traveling east is 30 miles per hour, and the rate of the train traveling west is 60 miles per hour. Now let's consider this problem. Two people are leaving the same place, but not at the same time. One leaves earlier, and one follows her at a later time. The problem is finished when the second person, the one who leaves later, catches up or overtakes the first person. Janice left her home at 9 a.m., driving her car at the rate of 50 miles per hour. At 10 a.m., her sister Lori drove after her at the rate of 60 miles per hour. In how many hours did Lori overtake Janice? Notice that Janice, who left earlier, has traveled for a longer time. We let x equal the number of hours traveled by Lori, who left later. The distances for Janice and Lori are the same because both of them left the same place and arrived at the same place. We fill in our table. The rates are 50 and 60, and we let x equal the number of hours Lori traveled since Lori left later. Since Janice left at 9 a.m. an hour earlier than Lori, Janice has been on the road for an hour longer, so her number of hours traveled is x plus 1. We multiply the rate and the time to get the distance, 50 times x plus 1, and 60x. Since the distances are equal, we set 50 times x plus 1 equal to 60x. We solve and get x equal to 5. So it took Lori 5 hours to overtake her sister Janice. If we want the number of hours Janice traveled, that's x plus 1, or 6 hours. If we want the distance that each girl traveled, we can substitute 5 for x into either one of the distance boxes, since the distances are the same. So it would be 60 times 5, or 300 miles, for Janice, or 50 times x plus 1, or 50 times 6, is also 300 miles. In our next problem, we are told that Sharon spends 6 hours on a trip out into the country and back. She rode her bike out at 4 miles per hour and walked back at the rate of 2 miles per hour. How long was the trip out? We set up our table labeling it out and back. The rates are 4 and 2. Now the total time for the trip has been given as 6 hours. But we do not know, however, how to break up that 6 hours. What part of the trip was going out into the country, and what part of the trip was coming back? To separate a number into two parts, we can let the first part be x and the second part be the number minus x. So in our problem, we let x equal the number of hours traveled out into the country, and we let 6 minus x equal the number of hours traveled back. We have separated the number 6, the full amount for the trip, into two parts, x and 6 minus x. To get the boxes, we multiply the rate times time and get 4x and 12 minus 2x. Since the two distances out and back are equal, 4x equals 12 minus 2x. We bring the 2x over to the other side and get 6x equals 12, or x equals 2. So the number of hours traveled out is 2, and the number of hours traveled back is 6 minus 2, or 4. The question, however, asked was how long the trip was out, or how long is the distance. The distance out is 4x, so 4 times 2 equals 8. So 8 miles is the answer. In our next problem, 2 people leave the same place at the same time and travel in the same direction. Steve and Sammy leave the same house at the same time and travel in the same direction at 5 miles per hour and 7 miles per hour, respectively. In how many hours will they be 6 miles apart? We set up our table. The rates are 5 and 7. Since they leave at the same time and finish at the same time, we let x equal the number of hours traveled by each of the boys. The distances are 5x and 7x. So 7x minus 5x equals 6 miles. 2x equals 6, and x equals 3. The number of hours traveled is 3 hours. So in 3 hours, the boys will be 6 miles apart. Now let us look at a mixture problem. A grocer's mixed nuts worth 60 cents per pound with nuts worth 80 cents per pound. How many pounds of each did he use to make a mixture of 20 pounds to sell at 75 cents per pound? It is useful to use a table similar to the table that we used in motion problems, but here there are 3 rows. The headings are number of, price per, and value. We label them 60-cent type, 80-cent type, and the final row is mixture. We fill in the middle column. The price of the nuts selling for 60 cents per pound is 60. We leave out the decimal point and do it in cents. The price per pound of the 80-cent nuts is 80, and the price per pound of the mixture is 75. We have been given the total number of pounds of the mixture, which is 20. We therefore have to break that 20 up into 2 parts. We let x equal the number of pounds of 60-cent nuts, and let 20 minus x equal the number of pounds of 80-cent nuts. To get the last column, we multiply the first 2 columns. We get 60x and then 20 minus x times 80, which equals 1600 minus 80x. 20 times 75 equals 1500. Now the final mixture is made up of 2 parts, so we add 60x plus 1600 minus 80x, which equals 1500. Solving, we get x equal 5. Therefore, the grocer used 5 pounds of 60-cent nuts and 20 minus x, which is 20 minus 5, or 15 pounds of 80-cent nuts. In our next problem, we read, 350 tickets were sold to a high school concert. Adult tickets cost 50 cents each, and children's tickets cost 25 cents each. How many of each type of ticket were sold if the total receipts were $142.50? We have to separate the 350 into 2 parts. We let x equal the number of adult tickets sold, and 350 minus x be the number of children's tickets sold. Multiplying the first 2 columns, we get the value, 50x for the adult tickets, and for the children's tickets, 25 times 350 minus x, or 8,750 minus 25x. The value of the tickets together was $142.50. Using cents, we write 50x plus 8,750 minus 25x equals 14,250. Solving, we get x equals 220. So, 220 adult tickets were sold, and 350 minus 220, or 130 children's tickets were sold. Another type of verbal problem is investment. Note the table on the screen. We label the first column, type of investment, the second column, the principal or amount, the third column, rate, and the last column is the income or interest. The principal times the rate gives us the interest. In filling in the principal column, we look to see if one of the investments is given in terms of the other. An example, one investment might be twice the other. In that case, we let one investment be x and the other investment be 2x. Another example of this might be when the investment says one investment is $500 more than the other. Here we let the smaller investment be x and the other investment be x plus 500. The other thing to look for in doing this column is to see if the total amount of investment is given. Suppose a problem says that $10,000 is invested, part at one rate and part at another rate. Then we divide the $10,000 into two parts. Remember, we separate a number into two parts by calling the first part x and the second part the number minus x. So we would have x and 10,000 minus x. Once we fill in the principal column, we multiply by the rate to get the income column. At this point, we read the problem to see what is told to us about the income. Have they given us the total income? If we know the total income from the two investments, then we add up the income boxes and set it equal to the total income. If we're told that the investments are equal, then we set the income boxes equal to one another. And if the problem says, for instance, that one income is $100 more than the other income, then we say one of those income boxes is equal to the other plus 100. In our next problem, Billy invested a sum of money at 8%. He invested a second sum, $1,000 more than the first, at 7%. If the annual income from the 7% investment exceeds the annual income from the 8% investment by $50, find the investments. We are given one investment in terms of the other. One of them is $1,000 more than the other one. So we let x equal the amount invested at 8%, and we let x plus 1,000 equal the amount invested at 7%. Multiplying the first two columns of our table, we get 0.08x and 0.07 times x plus 1,000 for income. This problem does not say that the investments give equal annual incomes. Here, the annual income from the 7% investment is more than the annual income from the 8% investment by $50. So we write 0.08x, the income from the 8% investment, plus 50 equals 0.07 times x plus 1,000, the annual income from the 7% investment. We get x equals 2,000. So $2,000 was invested at 8% and $3,000 was invested at 7%. The next type of verbal problems are age problems. This chart will help organize information given. We have labeled past, present, and the future. If Sarah is X years old now, what was her age 4 years ago? 4 years ago means we have to subtract 4 from her age now. So her age was then X minus 4. What will be her age 7 years from now? Well, her age is X now, so 7 years in the future is X plus 7. In our next problem, Mr. Jones is 3 times as old as his son. In 10 years, he will be twice as old as his son. Find their present ages. We will only be using two tenses, present and future, because this problem says in 10 years, which means 10 years from now, the future. We let x equal the son's present age. Since Mr. Jones is 3 times as old as his son, his present age is going to be 3x. In 10 years, Mr. Jones will be 3x plus 10 years old, and his son will be x plus 10 years old. At that time, Mr. Jones' age, 3x plus 10, will be equal to twice his son's age, 2 times x plus 10. Notice that in the equation, we are using the ages in the future. We multiply and get 3x plus 10 equals 2x plus 20. Subtracting 2x and 10 from each side, we get x equals 10. The son's age now is 10 years, and Mr. Jones's age is 3 times that, or 30 years. Our tape is an extremely useful learning tool, but it can't take your test for you. So do as many review problems as you can with pencil and paper. Now let's consider this problem. Betty is twice as old as Jennifer. 3 years ago, Betty was 3 times as old as Jennifer was then. Find their present ages. Why not push the pause button on your VCR and try this problem for yourself? We look at our table. We're going to use past and present, not the future, because the problem says 3 years ago, meaning the past. Jennifer is X years old now. Betty is twice that, or 2X. 3 years ago means we have to subtract 3. So Betty was 2X minus 3, and Jennifer was X minus 3. At that time, Betty was 3 times as old as Jennifer. So again, to make our equation, we use the ages of the past. And we say 2X minus 3, Betty's age, is equal to 3 times Jennifer's age, X minus 3. We multiply and get 2X minus 3 equals 3X minus 9. We subtract 2X and add 9 to each side of the equation, and we get X equals 6. So Jennifer is 6 years old now, and Betty is 2X, or 12 years old. Sally is 18 years old, and Natalie is 13 years old. How many years ago was Sally twice as old as Natalie? We fill in our table. The present age is now given. Sally is 18 and Natalie is 13. Our problem concerns the past and their ages then. Because we don't know how many years to subtract, we call that X. So Sally was 18 minus X, and Natalie was 13 minus X. We let X equal the required number of years ago. At that time, Sally was twice as old as Natalie, so again, using those ages, we set 18 minus X equals 2 times 13 minus X. 18 minus X equals 26 minus 2X, and solving we get X equals 8, which means that 8 years ago, Sally was twice as old as Natalie. Now to check, if Sally is 18 now, 8 years ago she was 10. Natalie is 13 now, and 8 years ago she was 5. And 10 is twice as much as 5. Now let's consider area problems. Each side of a square is increased by 4 feet. The area of the new square which is formed is 40 feet more than the area of the original square. Find the side of the original square. Each side of our original square is X. The area of a square is side squared. So the area of our original square is X squared. Our new square has an increased side, which is now X plus 4. The area of our new square is X plus 4 squared, which is X plus 4 times X plus 4. Multiplying, we get X squared plus 8X plus 16. To make our equation, we must remember that this new area is 40 more than the old area. So, X squared plus 8X plus 16 is equal to the old square's area, X squared plus 40. We subtract X squared from both sides and get 8X plus 16 equals 40. Subtract 16, we get 8X equals 24, and then X is equal to 3. So the original side of the square was 3. The new square has a side of 3 plus 4, which is 7. And to check, the area of the old square was 3 times 3, its area 9, and the new square's area is 7 times 7, which is 49. The new area 49 is 40 more than the old area 9. If you've been working for 20 minutes or more, perhaps it's time for a change of pace. Why don't you take a break? Relax for a moment. A very important topic is that of trigonometry. We will be working with right triangles. Every right triangle has its longest side called the hypotenuse, opposite the right angle. The other two sides are called the legs. They do not have to be equal. Besides the right angle in the triangle, there are 2 acute angles. Since the sum of the angles of a triangle is equal to 180 degrees, and we have a 90-degree angle, the sum of the two remaining acute angles must also add up to 90 degrees. In other words, they are complementary. We will name our three sides by the following three words: hypotenuse, adjacent, and opposite. Look at our picture on the screen. Let's make A a reference point. Side AC is the hypotenuse because it's opposite the right angle. Side AB is adjacent to angle A. Adjacent means attached to or next to. And side BC is the opposite side to angle A. In trigonometry, there are three functions: sine, cosine, and tangent. We abbreviate these terms using three letters. By definition, the sine of an angle is equal to the length of the opposite side over the hypotenuse. The cosine is equal to the adjacent side length over the hypotenuse length. And the tangent is equal to the opposite side over the adjacent side length. We can remember this by the old Indian tribe, Sokotoa. Sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. Here's our first problem in trigonometry. A 20-foot ladder leans against the building. The angle that the ladder makes with the ground is 37 degrees. Find how high up on the building is the ladder to the nearest foot. The first thing we do is draw a picture and label the sides. Now we put in the angle of 37 degrees, which the ladder makes with the ground. Our next step in doing this problem is to decide which two sides are involved in the problem. In this problem, the hypotenuse, which was the ladder, is 20 feet. And we are asked to find the height of the building, which is opposite the side of the angle, which is 37 degrees. Which function makes use of the words hypotenuse and opposite? The answer is sine. And sine equals opposite over hypotenuse. So in this problem, we're going to use sine. We write sine of 37 degrees equals the opposite side x over the hypotenuse, which is 20. So sine of 37 degrees equals x over 20. Looking up the sine of 37 degrees in the trigonometry table, we get 0.6018. We set 0.6018 equal to x over 20, and we cross multiply. We get x equal to 12.0360, and to the nearest foot, x is equal to 12 feet. A 70-foot wire attached to the top of a pole is tied to a stake in the ground. If the angle that the wire makes with the ground is 48 degrees, find the distance from the stake to the foot of the pole, to the nearest foot. Draw a picture. Which two sides are involved in this problem? Hypotenuse, because it's given the number 70. And the adjacent side to the 48-degree angle, because that's what they asked us to find. This leads us to use the cosine, since cosine equals adjacent over hypotenuse. The cosine of 48 degrees is equal to x over 70. Looking up in the table, we see that the cosine of 48 degrees is 0.6691. 0.6691 equals x over 70. Cross multiplying, we get x equals 46.837. To the nearest foot, x equals 47 feet. A ladder, which is leaning against a building, makes an angle of 28 degrees with the ground. If the foot of the ladder is 30 feet from the foot of the building, how high off the ground to the nearest foot is the top of the ladder? The foot of the building is its bottom. So, as we draw our picture, we see that we want to find how high off the building is the ladder. And that's x, with a length of 30 feet along the ground, and the angle being 28 degrees. We check the hypotenuse adjacent and opposite sides. We see that the two sides involved in this problem are the opposite x, because it's asked for, and the adjacent, because it's given us 30. Tangent equals opposite over adjacent. The tangent of 28 degrees equals x over 30. From the table, we find that the tangent of 28 degrees is 0.5317. So 0.5317 equals x over 30. Cross-multiplying, we get x equals 15.951, or 16 feet to the nearest foot. Now, let's carefully examine the next problem. Take a look at our triangle and find x. Which sides are involved in this problem? The opposite and the adjacent. We're going to use tangent. Tangent equals opposite over adjacent. We set up our problem. Tangent, 56 degrees, equals 20 over x. Notice that x is now in the denominator because it represents the adjacent side. The tangent of 56 degrees from a table is 1.4826. We set this equal to 20 over x and cross-multiply. However, we now get 1.4826x equals 20. And to get x alone, we have to divide 20 by 1.4826. This may prove to be a bit difficult. In this problem, there is an easier way. Here is a trick with tangents we can sometimes use. When x is in the denominator and tangent is the function that we choose because we're working with the adjacent and the opposite sides, we can use the other acute angle of the triangle. Since the two acute angles add up to 90 degrees, 90 minus 56 equals 34. Notice that for 34 degrees, the adjacent and the opposite sides switch positions. The tangent of 34 degrees will be equal to x over 20. The tangent of 34 degrees is 0.6745, and this is equal to x over 20. Cross-multiplying, we get x equals 13.490, or 13 to the nearest integer. This is certainly easier than dividing 20 by 1.4286, and we will get the same answer both ways. Note, if the problem has x in the denominator and we use sine or cosine, we cannot use a similar trick of using the other angle. It will not help, and we'll just have to do the regular division. Some problems contain the term angle of elevation. An example of this would be a person looking up at the top of an object, say a pole or a tree or a building. The angle that is formed by her eyes looking straight across and her raising her eyes to look at the top of that object is called the angle of elevation. For example, from a point 50 feet from the foot of a pole, the angle of elevation of the sun is 41 degrees. Find the height of the pole to the nearest foot. We are looking at the sun over the pole. The angle of elevation is on the bottom of the diagram, rotated from the horizontal at 41 degrees. The pole's height is labeled x since we want the height of the pole, and 50 is along the ground. We use tangent. It equals opposite over the adjacent. The tangent of 41 degrees equals x over 50. Looking this up in the table, we find that it's equal to 0.8693. So 0.8693 equals x over 50. Cross-multiplying, x is equal to 43.465, or 43 feet to the nearest foot. So far, in all of our problems, we have been given one side of the triangle and an angle. We have been finding a second side, whether it was the adjacent, the opposite, or the hypotenuse. Here we have a problem where we are given two sides of the triangle and are asked to find an angle. There are two sides that have numbers involved in our problem, the opposite and the hypotenuse. That's sine, and sine equals opposite over hypotenuse. We write the sine of x degrees equals 40 over 70. We reduce the fraction, if possible. In this case, we get 4 over 7, and divide the bottom number into the top. 7 into 4 is 0.5714. We want 4 decimal places because the table is given to us in 4 decimal places. So the sine of x equals 0.5714. Now we look this up in the table in the sine column. The closest one to 0.5714 is 0.5736, which is the sine of 35 degrees. So x equals 35 degrees to the nearest degree.